Hi, welcome to GCP GroundSchool. This session is about Google Cloud Networking. My name is Haider Witwit. I'm a customer engineer, networking specialist with the Google Cloud public sector team. I've been with Google for a little bit over 1 year now. During this time, I've been supporting Google customers to build and design their networking solutions on Google Cloud. Prior to joining Google, I was a solutions architect with AWS, also supporting their public sector team. And prior to my cloud experience, I was a full-time network engineer. And at that time, I was building and maintaining physical data centers. This mixed experience and background helped me better understand customer pain points and how to address in their cloud solutions. During today's session, we're going to touch on multiple things. So our agenda will include talking about Google Global Network. This is the network that we use to deliver our cloud services and other Google products. And then we'll talk about the Google VPC. This is the virtual network space that customers create in the cloud and use to enable routing and access to different services. After that, we're going to talk about Cloud DNS, which is the managed DNS service that Google provide for GCP customers. Then we'll talk about the hybrid connectivity options that enable Google customers connect their Google networks to external networks outside of Google Cloud. This can include on-premises networks or possibly VPCs. Their VPCs provisioned in different cloud environments. Around the end, we're going to touch on Google Cloud Load Balancing, which is one of the core networking fundamentals of Google network offering. And at the end, we will see how we can use the things that we learned to build reference architects. So we're going to touch on 3 common reference architectures that our customers use on their Google Cloud deployments. Okay, well, let's get going with Google Cloud Global Network. Google infrastructure spans across 24 regions. Those are generally available regions in different geographical locations. In these regions, we offer compute, networking, and storage resources that customers can provision. In addition to those 24 regions, we have 9 regions that are in the work, and they will be available in the near future. Each one of these regions consists out of at least 3 zones. These zones are independent data centers or a group of data centers that are highly interconnected with each other. They have no dependencies between these data centers, and the idea is to enable the Google Cloud customers to build highly available solutions within a region. To address unlikely situations of a single zone failure. In addition to these regional data centers, we have network edge locations, about 144 network edge locations. These are point of presence where Google have hardware to enable customers connect to Google services. This is what we basically will explain with the interconnect service and how customers can connect to Google service through the service. In addition to that, we have more than 200 POP locations that we use for caching purposes, distributed across countries and different territories. All of these locations are really connected through hundreds of thousands of miles of Google fiber. In a way that we can always route this traffic using Google managed network and never need to route traffic over internet. With Google, there are 2 network tiers that customers can choose from. There is Premium, and in the case of Premium, we try to keep traffic as much as possible on Google backbone and only get to the point that's as close as possible to the user to deliver the packet. What this will benefit the customer is more advanced network experience, because the traffic will be routed over less number of hubs and over a network that's more reliable, more bandwidth, and eventually provide the customer with a better network experience. Usually, customers with network-sensitive applications can leverage the premium tier. The standard tier is similar to the network experience you get with other cloud providers, and in this case, we use what we call in the networking world hot potato routing. What that means is that the traffic will try to get on the internet as much as possible, and then majority of the trip will be routed over internet to the end user. The impact, as it's clear, is that you're going to have more number of hubs impacted by also the internet weathers. Customers usually who have applications that are less network sensitive usually go with the standard service offering. Talking about Google Cloud VPC, VPC by itself is a common concept, and the idea here is that customers want to create their own virtual private network in the cloud. So this is their virtual space in the cloud where they control the addressing and routing within that boundary. With Google, our VPCs are owned by a project, and the VPC by itself, you can think about it as a global container for a group of networks. So the VPC by itself does not have a network range. The network ranges are assigned to what we call subnets. These subnets live within a region, so they span across all of the zones of a region. Customers can have multiple subnets in a region, and with every region where they want to provision compute resources, they will need to provision a subnet there. Subnets can have will need to have a private range. This is an RFC 1918 or non-RFC 1918 range, and they can also have additional secondary network ranges. Routing between these subnets are already taken care of by Google. So all of the subnets that belong to the same VPC is routed by default, and customers, of course, can create firewall rules to lock down the environment. For customers who want to create multiple VPCs, usually for use cases where they need network segregation, we provide a capability to peer VPCs together. This is what we call VPC peering. VPC peering is managed, is completely managed by Google, so there's no bottleneck, there's no additional delay or cost to use this feature, and it can be used to advertise all of the subnet ranges, all of the VPC ranges, and additional to that, we also support custom route advertisement. The benefits of using custom route advertisement significantly show and simplify architects that need to build hub and spoke models, which we're going to explain shortly in the reference architect slides. As I mentioned, VPCs belong to one project. However, there are use cases when customers need to centralize their network administration while utilizing these resources by multiple projects. So for these use cases, we support a shared VPC concept. The shared VPC, in this case, you will have a VPC that's owned by one project, one team of network administrators. They will take care of creating the subnets, the network ranges, the routes, firewall rules, etc., including the connectivity to on-premises. So in this diagram, for example, we're showing a VPN connection from that VPC to an on-premises facility. These subnets can be shared with other projects. So in this case, you can think about the host project as a project owning that VPC, and the service projects as the projects that consume these VPC resources, subnets to be more specific, to create VMs and utilize that IP space. And eventually, all of these VMs will be able to access the resources available in the host project, VPC, like firewall rules, and VPN connections. This is really common design architecture that we have seen a lot of our customers adopting when network segregation between the VMs is not a requirement, because eventually all of these VMs will live in a single VPC, but they are utilized by multiple projects and administrated by a single networking team. When our customers need to deploy a capability that's not natively supported with Google, for example, IPS/IDS functionality or deep packet inspection or next generation firewall, they bring a network appliance from our marketplace. So all marketplace have a number of the common networking providers with their softwares like Cisco, Palo, and others, and they deploy it in their VPC and use a multi-network interface approach to enable connectivity to multiple VPCs. So the idea here is that each one of these VPCs will host one network interface for the appliance, and this appliance will sit in line for the east-west traffic and north-south. The idea behind sitting it in line is to be able to see the traffic and act on the traffic based on the security capabilities it provides. Okay, switching to the cloud DNS topic. Every machine in the cloud will automatically point to what we call a metadata server. So the DHCP setting of the machine will use a metadata server as a DNS resolver. So all of the name queries goes to the metadata server, and this server will enable internal name registrations. These are things managed by Google within the project. Customers doesn't have to worry about that. But the benefit here is that this metadata server will enable integration or the use of our cloud DNS service. Our cloud DNS service is a highly available and scalable service that comes with 100% SLA, and it offers customers the creation of a private or public DNS zones. In the case of private zones, when customers create these zones and create the records in the zone, they associate that zone to a VPC. Now, machines in that VPC who use the metadata server for name resolution will be able to look up these zones in a certain order and enable them to make name resolutions based on the records created in that zone. Of course, usually when you operate in the cloud, there are multiple DNS architects that the customers may want to support. So, for example, we have customers who want to forward all name queries to a DNS server that they manage. For that, we provide a feature called outbound policy. And in this case, outbound policy, the customer will provide a list of IP addresses, and all of the name queries will be forwarded from that VPC to that DNS server. For use cases where the customer want to enable remote DNS servers or remote networks to make inbound calls to the cloud DNS, we enable a feature called inbound policy. For use cases where certain zone need to be looked up on another DNS server, you can think about it as a conditional forwarders. We have what we call a forwarding zone, and a forwarding zone is a configuration where you say for all of name resolution request for that specific domain, send it all to that IP address. And that usually this is really common with like AD servers when you have an Active Directory integrated DNS and you just want to forward all name queries to that domain to that specific DNS server. So we support that through the use of forwarding zone. And in the cloud, because our customers really use multiple VPCs typically, with the way we enable a centralized DNS resolution strategy is through the use of DNS peering. DNS peering in a nutshell is the capability to let one VPC use the name resolution order or zones of a different VPC. And this is, of course, is outside of the data plane. This is a control plane functionality. So think about a centralized model where customers want to manage DNS on a single VPC while enabling a group of other VPCs to use that DNS for or that VPC configuration for all of that DNS setting. Okay, so moving on to the hybrid connectivity. Hybrid connectivity is about services that we offer our customers to enable them to access their cloud networks from outside of Google Cloud. Three primary services that we provide for this use case. We have an HAVPN, that is a managed VPN service, typically over internet. We have Cloud Interconnect that will enable customers establish dedicated connections to Google Cloud. And we have peering that will enable the customers to have a direct peering between their public network and Google public network to be able to route that traffic over optimized connection rather than internet. This is really common to access Google public services like workspaces or our Gmail service. All of these services are really accessible, can be accessed over peering instead of internet. So starting with Cloud VPN, this is a VPN managed service in the cloud. On the Google side, we have managed endpoints, IPsec connections that are terminated on the other side on a supported BGP device that also need to support, of course, IPsec. We support IP version 1 and version 2. This is a highly available service, so it comes with 2 tunnels. Each one of these tunnels support up to 3 gigabits per second throughput, and more throughput can be leveraged through creating multiple tunnels and use ECMP, BGP, equal cost multipath, to equally distribute traffic over multiple tunnels where more throughput is needed. The dedicated interconnect service will enable customers to have a dedicated connection to their VPC. The service is offered through Google hardware that is available in list of locations. These are the Meet Me locations that Google published. What the customer needs to do is that they can either meet Google in these locations by having a presence in there or working with their telco provider to extend their connectivity to their data center, physical data center. By working directly with Google, they can get 10 gig or 100 gig connections. And then once they provision these connections, they create what we call VLAN attachments. These VLAN attachments is a BGP session that's terminated on one side on their router and on the other side on the cloud router within their VPC. We actually support, we have best practices to support 3 nines of SLAs or 4 nines of SLAs. Our recommendations is always to connect 2 different zones in a single facility, metro facility, so that this will assure a zero network disruption during maintenance windows where Google will not really kind of do maintenance for 2 routers, 2 different zones at the same time. If customers cannot meet Google in the list of locations published, or want to get less bandwidth, like subsets of the 10 gig port speed, they can work with a partner. And in this case, partners have already established these connections to Google. They have presence in different locations, and they will work with the customer to extend this connectivity through the last mile access. And they will provision or enable the customer to provision these VLAN attachments. And the same model will work. In this case, an edge device on the customer side that will terminate the session, and cloud router on the other side, on the customer side, to terminate that on the Google side. This is what we call the layer 2 model. There are situations where the partner provide a layer 3 service. In this case, the partner will terminate the BGP session on their device and extend that connectivity to the customer's premises through MPLS or point-to-point connectivity. Of course, this service model also comes with 3 nines or 4 nines SLA support, but in this case, this support will come from the partner, not Google. Cloud load balancing is really important when we talk about networking. With Google, we provide multiple options for load balancers. These options really depends on a number of factors. First of all, whether the application is internal, means it needs to be accessed from a private network or from VPN or interconnect or from within the cloud only, or external, which means that it can be accessed from really anywhere over internet. The port, the type of traffic, whether it's TCP, UDP, or web traffic, the scope, the geographical scope. What that means is that you want your load balancer to reside in a single region or in a global multi-region mode. The network tiers, if you want the premium or the standard, as we touched on earlier, the difference between these 2 network tiers. And eventually, if you want that load balancer to be proxy-based or pass-through, which is really important usually when customers need to be able to see their request IP address. So 2 load balancer types that I wanted to maybe a little bit get into more details. The external global HTTPS load balancer is core building block in our global strategy. So this is the HTTPS load balancer. It's global, so when customers create that load balancer, they will get a single public IP address. The load balancer supports to have backends on in multiple regions. So we do anycast to see where the request comes from, and then try to map it to the closest backend to the requester to maintain lower latency. So in this diagram, we see people or users in Singapore or New York or California. When they request that single IP address, we as Google will map that traffic to the closest backend to maintain that lower latency. And within the load balancer itself, the HTTPS load balancer here, we have embedded number of capabilities. For example, SSL offloading using customer managed keys, DDoS protection using managed WAF with our Cloud Armor service, CDN for content delivery and expedite delivery, and a number of other security services. The other type of load balancers I wanted to touch on is the internal TCP UDP load balancer. The use case for this load balancer is a little bit different. It's really used to enable high availability HA deployments in the cloud for networking appliances or for applications that does not use web traffic. So the load balancer is highly distributed and available within a region. It uses a private IP address from the VPC space. It's accessible internally within the same VPC or through VPN or interconnect. And the backends are in the same region, and where the load balancer will only forward traffic to the healthy backends. It supports active standby configuration, and it can run in multiple layers within your application in the cloud. So really a primary building block for any HA deployment in the cloud. Great. So now that we have touched on a lot of networking concepts, we want to see how customers use these networking blocks together. So I have 3 reference architects to talk about here. The first one is really a hub and spoke model where customers will create a single VPC for common services. So this is the VPC in the middle in green. They will build connectivity to on-premises from that VPC. So you have redundant interconnects or VPN attachments. And then they will extend this connectivity to other spokes VPC using VPC peering. So of course, this VPC in green is going to have the DNS rules, the firewall rules, or the DNS zones. And with VPC peering, if you recall, I said that customers can advertise custom routes, which becomes really helpful here to advertise the on-premises networks. So the on-premises networks are learned over the interconnects attachments and then extended through VPC peering to the spokes VPCs. These spokes VPCs can represent prod, non-prod, or different projects, and they can be either standard VPCs or shared VPCs if the access need to be extended to other service projects. So this is a common design model, provide network segregation, but one of the limitations of this design is that there's 2 spokes here, the blue and the red, cannot talk to each other through peering because VPC peering is non-transitive. So for use cases where the customers want to enable VPC peering, they can use our Cloud HA VPN offering, which in our case, it does support to connect 2 VPCs together using a VPN managed endpoints on both sides of the connection. And of course, this is supported through 4 nines of SLAs. And because you'll have a BGP session in here, this is going to give customers more granular control into what gets advertised and enable the spokes to communicate directly to each other, of course, through that common VPC. A different design approach is when customers want to deploy that third-party appliance or a marketplace appliance. So what I'm showing here is that multi-NIC deployment approach, multi-network interfaces approach, where you have one interface in an external VPC. This external VPC represents the VPC that talks to external networks over internet or over interconnect attachments or VPNs, and then another interface to an internal VPC. This internal VPC will extend connectivity through VPC peering to multiple of consumers' VPCs. We call them here as spokes. Now, this design model can really scale to more than 150 spokes VPCs when you create multiple internal VPCs. And this is really before you need to provision a different set or 2 more pairs of these appliances. As you can see, we deploy the appliances in pairs, and there are load balancers on each side of the connection to make sure that there are no single point of failures in here. There's an optional management VPC or management network. Depends on the vendor if they want to use that kind of out-of-band management model. And this deployment model is really common, and when customers use these appliances to deploy, IPS, IDS, or next generation firewall capabilities. Okay, so this brings me to the end of the presentation. I want to thank you for your time. I hope the session was informative. Please stay tuned for the next security session, and we appreciate your feedback to help us improve this event in the future. Thanks again.